Okay, so there's actually a website where you can go in and try and extract tomography profiles across the Earth. So they've taken data collected throughout the Earth, they've put it together in this model, and you can go extract profiles from it. So in the web browser, you type in Hades Underworld Explorer, and sorry, I shouldn't have clicked on it. There's two options that come up here. There's actually three. Just to warn you, please choose the one that's got the numbers 136.144. They might have fixed these websites, but in the past I've struggled with them and just the picture's not coming up. So I use this one here, the top one. Click on it. And so this is the website that comes up. And I'm not sure we can, yeah, so control scroll to zoom. So I can zoom out across the Earth. And you can see at the moment this L to R is our profile. And so it's going through Indonesia. And if you scroll down here at the bottom, it's giving you the tomography image across this profile. So this is the left over here, this is the right. And so you're seeing reds and blues. So what does it mean? Remember, you watched in the video. The reds mean it's the velocity of the seismic waves going through this material is slower. This is most likely because it's warmer or due to changes in composition. Whereas blue is faster velocity, usually due to colder material. And so here we're actually going across the subduction zone here on both sides of it. And so the subducting slab, remember you learned that is the cold material. And that is why, because it's from the oceans, and that's why it shows up as blue. Remember that obviously this is the surface of the Earth. Down here is the core mantle boundary, which is about 3,000 kilometers. And these lines, if you can zoom in on your computer, there's two thin white lines. You can see it says 410 and 660. These are layers in the mantle, because this is the mantle here, that we'll learn about in class. And you can see how this 660 is kind of where the subduction zone is flattening out here. And so there's a lot of detail shallower near above the 660. Below that, the data and the coverage by the ray parts, so the energy traveling through, isn't as good. So we don't get as high resolution, and it's just so deep. And so it's a little more blurred out. Whereas, in the shallower regions, it's easier to see a little bit more detail, but it's still quite blurry. So this is this plate boundary. How can we move this? So if I click on this L and I move it to the L of my profile, and I click on this R and I move it, and let's pretend we're looking at the East African Rift Valley here. So you can see here it's not as interesting really, but you can see this region here is where the East African Rift Valley is here with my mouse, and it's a little bit more red than the yellowy and the blue, the greeny surrounding area. So this is probably the plume coming up here. Remember, it's rising up off of the LLSVP at the core mantle boundary. I can't confirm whether this is the LLSVP. The resolution's not good enough in this data, but it could be that it's rising up here to the East African Rift Valley. And so you can really go and do that across all the different plate boundaries. Don't get confused. I currently on my screen have zoomed out a bit too much, so you can see I've got two North Americas. So let's see if I zoom in a bit. We'll resolve that issue. So I've now got my profile across South America, and we're expecting to see the subduction zone here, and you can see it there, the subduction zone. You can click on this Cartesian view, and it kind of flattens it. It can make it a bit more difficult to see, but the one nice thing is if you scroll your mouse over it, it actually gives you depth values and percentage values, and jumps you up and down on your scale bar on your right hand side here. So it can be quite helpful, but in some cases not. I do find making your line a bit longer makes it just a bit easier to see rather than squashed. I'll show you what I mean. If you do a short profile like this, you can still see your subduction zone, but it's not as clear to see it compared to the surroundings. So rather extend your profile a little bit. So try do this for your plate boundary. Maybe you won't see anything, maybe you will. Just see what data you can get out. You're also welcome to just Google and try see what if anyone has done a study over your area, getting higher resolution tomography data. So I mean, this is the tomography over South America. If I went and typed it into Google, tomography South America, I'm just going to write subduction. Let's go here to images. There's actually a lot higher resolution data. I'm just trying to find it here. Might be that one. I know that the angle of the subduction zone actually changes in the region. Could be this one. Just triple checking if not something else. But yeah, I mean, they've done a lot of studies across South America. Could try zoom into this one. Let's just look over here while that's loading. So you can see they've taken a number of profiles across the west coast of South America, going slowly down, and the angle of the subduction is changing. You can see here, no longer is it going from surface down to the core mantle boundary, it's going down to the 660 or 670 discontinuity, and there's quite an unusual changes in shape in the subduction zone. It does blur out a lot here. Like here, it doesn't mean that the subducting slab is everywhere here. It just means the data is not that good at resolving the slab. But you can see here there's a bit of a steeper dip here, whereas here it's maybe a bit shallower. So it can be quite complicated if you then go do high resolution studies. So you're welcome to see if anything's been done at your plate boundary. It won't have been done everywhere, especially in the oceans. But yeah, see if there's anything available.